All right, so IVT is something we did in Unit 2, Intermediate Value Theorem. If you remember that one, these are similar, that's why I'm going on. That one said, choose two endpoints. Your function, as long as it's continuous, differentiable on this closed interval, then it must take on all y values between here and here. Oh, I'm sorry. I'm doing it again. I'm sorry with the graph. It must take on all y values between here and there. It could go higher and lower, but it must take on the values in blue there. That was the IVT from UT. It's about continuity. The MVT is different but related. So you'll see some similarities. In order to show you what the MVT says, here's what I want you to do. Is find an open spot, on that page. There's plenty of room on page 3 if you want to flip back. I think. Well, on mine there was. Yeah, well, whatever you want. Just find some space. We did this for IVT, a similar illustration. So here's what I want you to do on this one. You will draw 2 points. And what you're going to do, I'm going to give you some conditions for this. You're going to connect them with a curve. Right? You're going to connect them. Now, it could be a straight line. That would be pretty boring, though, if you do that one. So I encourage you to make it more curvy, up and down. Here are the conditions when you draw this curve. Make sure it's a function, so it can't go backwards. Okay, that wouldn't pass the vertical line test. Make sure it's continuous, so don't stop there and pick it up here. And finally, make sure it's differentiable, so it can't have a corner or a cusp or, again, a discontinuity. So just connect those 2 points with those conditions. You draw 2 points? See that? You kind of went backwards.
How big is this space?
You know what I mean? Like, it looks like it kind of. So that's what I'm going to do. So once you have that down, your 2 points, doesn't have to look like mine, just could. Something similar. Okay. She just did just a little loop, just that's it. Well, that'll work. It'll work. Here's what you're going to do next. You're going to draw in the secant line. Remember, the secant line is just the line that connects your 2 points, a straight line. Straight line between your 2 endpoints. Then here's the goal. This is what the mean value theorem, here's where we get to it. Can you find tangent lines? So remember, like a tangent line would be like this, intersect at 1 point, right? Secant line goes through 2 points. Tangent line is slope at 1 point. Can you find and draw in a line with the same slope as your secant line? So that's what we're going to try and do. The goal: draw in other lines, or maybe one that would be like this. That has the exact slope as that one. Yeah. Here's what I said. I bet you can find at least one. Actually, the MVT says there will be at least one.
Where? I did it.
You did do it. Good job. There should be.
Like right here?
Yeah.
Really?
There should be.
Where?
Well, I'll show you on mine in a minute, but I want you to do yours.
You don't have to like solve for me.
Nice.
You just draw.
No, I just want to draw a line.
Where?
I'm crossing it out. Where would the tangent line be that would have the same slope? Let's get rid of that. Why are you blocking this?
Is that it?
Look at that back there. What?
Mr. Hunt. Is that it?
That is it.
You were right. She was
Why
right.
are you guys so hesitant? If you're wrong, it's okay. So here's one of mine. At this point right here, again, I was a little sloppy. At that point right there, it looks like probably about this point right here, the tangent would be there. Tangent right here. It looks like I have another little one right there. I had 4 points where the tangent line would have the same slope as that secant line. You have a couple more in that one, but yeah. So, do you know why I said at least one? MVT It guarantees that the secant line slope and the tangent line slope must be equal at least once when these conditions are met. That's what it says.
Wait, what if you had a straight line?
Hold up. In other words, average rate of change is the secant line slope must equal the instantaneous rate of change slope, the IROC, at least one time. So here's the mean value theorem in the easiest way. The AROC equals the IROC at least one time. Could be more. Mine was 4. If it was a straight line, then your secant, then every point along here is the tangent line is the secant line. That's why it would be pretty boring to do. Or some people up here just did like they did this single curve, and so only
Some.
one person. Yes. Did you have another question?
Me?
Yeah.
No, Eric.
Sorry.
Is this like hand up?
Yes, above the torso. So Aiden has a hand raised.
No, it should be above the head.
I think it needs to be an open hand above the head.
Exactly.
What if I just want to be like, I kind of want to answer the question.
No
I'm
one
not
asked
sure. This is like.
If you're not sure, then don't answer.
No, I disagree. You should try and answer. All right, back to this. Here's the illustration. These 2 points, here was the secant line, there's the tangent line slope. Again, it has to be, I said all that in words up there. Has to be 3 things though. Continuous function, has to be a closed interval, and has to be differentiable. Those 3 things. Then it will work. Then what will happen, I said this as well, the IROC, the instantaneous rate of change, equals the mean rate of change, that's the average rate of change. So there you go, the IROC equals AROC. Now, in a math terminology, here we go, derivative is IROC, F prime. Do you remember this as average rate of change? F of B minus F of A over B minus A? That was unit 3.
Oh, yes.
So long ago. So it's the math way of saying AROC equals IROC. Oh, yes. All right, well, that's it. Now we'll see some examples of it, and yeah, we'll talk through some examples of it. What can I answer, though, before we try some? Very well. So let's find all numbers C satisfying the conclusion to the mean value theorem for these 2 functions. C is just the common variable. It's really just x. So as you see up here, they call the function C. It's basically they replace everything with C, and then.
Why do they replace everything with different variables when they all mean the
I
same?
think just to represent the change in it. That's not. We're not trying to do something with the original function. We're trying to look at change. I'm not too sure, honestly. Like here, this is well, it's the x coordinate C. They need a new. I guess they could say x, but it's because the function here has x in it. That's probably why.
Okay.
So let's call this one C, so it's different from that x. Okay, so what we're doing here, find all numbers C. We're finding this. Where at C, at x equals what value was the average rate of change equal to the instantaneous rate of change? That's what we're doing. These problems boil down to conceptual ones, like down here, or algebra ones, where we literally do this. AROC equals IROC. Now, before I do that, I do need to check the 3 conditions. So let's go through this. First of all, is this a continuous function? Any breaks in that polynomial? No. Any polynomial? It's continuous everywhere. Is this on a closed interval?
Yes.
Yeah.
Yes. Is this function differential anywhere? Like, is there any corners or? No, there are not. It is differential. So we can do this. The AROC, f of b minus f of a over b minus a. So let's do that one first, where b is 3 and a is 0. So f of 3 minus f of 0 over 3 minus 0. 3 minus 0 is 3. F of 3, we're going to plug in 3. 3 squared is 9, times 2 is 18. Plus 3 times 3 is 9, so 27. When I plug in 0, f of 0 will be 0 plus 0 equals 0. So you get 27 over 3, which is 9. I'm now going to do the IROC. It's just the derivative. So again, here's where they really do f prime c. But I'll just do f prime x, the derivative 4x plus 3. Last thing is just set them equal. So this is the average rate of change slope. So it's kind of this diagram. What we just found is the slope is 9. We found the derivative function is 4x plus 3. We're going to find where the derivative function slope is 9. And that'll give us this coordinate, right? This c or x. All right, so I just set 9 equal to the 4x plus 3. Subtract 3, I get 6 equals 4x. Divide by 4. 1.5. By the way, you'll notice it's halfway along the interval, 0 to 3. That is just coincidence, and it will not always just be half. It just happens. So again, what we found is basically right here, 1.5. That was the x coordinate where the slopes were equal. Let's do another one.
I'm disappointed.
I can't hold on to it today.
I expected more.
I'm sorry. I am. I think you missed it when were you not in here?
What happened?
We talked about the time
Oh yeah, he finally wore time.
I don't know where I was.
So yeah, it was kind of for a while. Let's do part B then. Let's look at the conditions again first. I'm gonna write close first this time. So it is very important. If these conditions are not met, you cannot do the MVT. I went closed interval. Thank you. Yes. Is this a continuous function? Well, square root of x is this. 2 times square root of x just makes it go up faster. So it's continuous. Yeah, we're on 1, 9. So this is a good question you might be thinking is like, well, what if we were on negative 1 to 9? Well, it doesn't even go over there. It's not in the domain, so we couldn't do that. So that wouldn't work. But yeah, we're on 1 to 9. So that's good. Is it differentiable? Like, is there any corners, cusp, discontinuity? No. So we can do the mean value theorem, where we will know that AROC equals the IROC at least once. So let's do the AROC, f of 9 minus f of 1 over 9 minus 1. So f of 9, the bottom's 8. F of 9, I plug in 9. Radical 9 is 3, times 2 is 6. F of 1, I plug in 1. Square root of 1 is 1, times 2 is 2. So I get 4 over 8, which is 1/2. Okay, now I need to do the derivative, and I will set it equal to that. Equal to the 1/2. So the derivative, g prime x. Well, let's see. This, if you remember, square root of x, we have to change it to the half power. It's 2, change x to the half power, and then do power rule. So really, I bring the 2 down. This 2, coefficient. Well, I guess I don't need to. I can just do power rule and cancel out. So I'm doing power rule. It's 1/2 x to the negative 1/2. If you had done the power rule like 2 times a half, it would already cancel out. That's fine. Like this. 2 times a half is 1. So. Anyways, I'm just left with it. I'm going to change it back to a positive exponent. 1. There's still 1 left in the numerator over x to the half. I'm going to do one more thing. Let's make it square root of x, because x to the 1/2 is really square root of x. Finally, I will set the AROC 1/2 equal to the IROC function 1 over radical x. And really, the numerators are equal, so I'm really setting the denominators equal. I'll do this. 1 times cross multiply. 1 times radical x is radical x. 1 times 2 is 2. Square both sides, so we get 4. So let me draw a little illustration. Square root of x is like this. Well, it keeps going up. That wasn't great. But 1 to 9, we found basically this. The slope there was 1/2. And we just found at x equals 4, so right here, that the slope was also 1/2. So those are some good algebra questions. I got a few others, a little more conceptual, but similar idea. Anything I can answer on those two? Very good. Let's look at the bottom. Explain why the MVT fails on the interval -1, 1 for the functions. So each of these, I'm going to check the 3 conditions, and we're going to see that at least one of them is not going to work. Yes. So let's look at A. So we know that it's an absolute value, right? But it's moved down 3. So it's like this bottom one here. It's an absolute x or absolute A minus 3 is. Just so you have an idea. Now we're on the interval -1, 9. So are we on a closed interval?
Yes.
Yeah. Is this a continuous function?
No.
No.
Or yeah, it is.
Yeah, there's no breaks in the graph. No breaks in the graph. Is it differentiable?
No.
No. Why?
There's a corner.
There's a corner right there. Yeah. So explain why the MVT fails. And by the way, we're only on, here, I'll say this in -1 to 1. So we're like in between. We're at this part of it. Explain why. You could say not differentiable. Yeah. Explain why. Because they tell you it fails.
Yes.
Not differentiable, I'll put corner
What corner?
at x equals 0. Or a equals 0, I guess. Now here was a good question from earlier. Somebody said, well, what if we were on the interval 1 to 4? So is this part of the line? Yeah, it would be good. We could do MVT. But, because there is no corner in that interval, but -1 to 1 does not work. Alright, let's do B. Again, I'm going to check these. Closed, continuous, differentiable. In B, I have a piecewise function. We're on a closed interval.
Yeah.
-1 to 1, yes. Is it continuous? How do you know?
You have to plug it in.
Yes.
You got to plug it in. I don't even know. Let's good, right? Because we got to plug in 1. I should say each of these functions are polynomials, so they're continuous everywhere and differentiable everywhere, except possibly where they meet. So let's see. I don't know. Let's plug in 1 and see if they're even continuous. 1 cubed is 1 plus 3 is 4. Plug in 1 here. 1 squared is 1 plus 1 is 2. So it is not continuous. And therefore, actually, if it's not continuous, it can't be differentiable. So why explain why it doesn't work? I will say not continuous at x equals 1. That's span.
Might drop.
Okay. Any questions on those? Why it doesn't work?